Hey guys, Miss Gosling here. In this video, you're going to learn about electricity. By the end of the video, you'll be able to solve problems involving electrical forces and fields. So let's go ahead and get started. So the electric force equation is pictured here on the screen. The electrostatic force is equal to K, which is Coulomb's constant, times the charge of each charge, Q1 and Q2, divided by the distance between the two charges. Now, a couple of notes here. First, this equation is usually known as Coulomb's law, and that is because he is the first person to derive this equation and publish a paper with the equation in it. The second thing that's really important to know is the units for all of these symbols. So, of course, electrostatic force is a force and therefore measured in newtons. We measure charge in coulombs, which we use the capital C to represent. And we measure distance, of course, in meters. So the only new unit here is capital C for coulomb, which again, we use to measure charge. Before we go any further, I do want to take a moment to talk about electrostatic attraction and repulsion, and a little more specifically about charges. So one key difference between gravity and electricity is that in gravity, objects can only have positive mass. There's no such thing as a negative mass as far as we know. So when we are measuring mass, every single mass is positive and every single gravitational force is attractive because two masses will always be attracted to one another. When we talk about electricity, on the other hand, we are now talking about multiple different types of charges. So you guys, I hope, have heard of both protons and electrons. These are my two kind of fundamental elementary charged particles. And as you hopefully remember from chemistry, our electrons are negatively charged and our protons are positively charged. And this is a feature that continues throughout the rest of electricity. Whenever we're discussing electrostatic charges, they can be either positive or negative. And they can have values of any multiple of the elementary charge, which is the charge of the electron or the proton. The other thing that's really important to know then is because my charges have different signs, those signs represent different directions. And when we talk about electrostatic forces, we need to know, are the two particles going to be electrostatically attracted to one another or repelled by one another? Because in electricity, we can have both attraction and repulsion. So to summarize, charges can be positive or negative, and unlike gravity, where the force is only attractive, with electricity, we can have either attraction or repulsion. So let's take a look, and the key rule here is like charges repel and unlike charges attract. So if my two charges have the same sign, regardless of whether it's positive or negative, they will be repelled by one another. If it's different signs, they'll be attracted. So my two negatively charged electrons here are going to be repelled by one another. My two positively charged protons will also be repelled by one another. For my middle two charges, however, I have one negative charge and one positive charge. These two are opposite, and so they will attract, like so. And so again, the key is my like charges go away from each other, and my opposites attract. The other thing I want to discuss before we get into problems is something called the elementary charge. The elementary charge is the magnitude of charge on either an electron or a proton. So electrons and protons have the same charge but opposite signs, with electrons being negative and protons being positive. Both have a charge of 1.602 times 10 to the negative 19th coulombs. And when we talk about the elementary charge, we will often use the letter E to represent it. So, for example, the helium nucleus has a charge of positive 2e because it's made up of two protons and two neutrons, and those two protons each have the charge of one positive elementary charge. So to find the charge of an He nucleus, I would do, that's plus 2e, which is 2 times 1.602 times 10 to the negative 19th coulombs, or 3.204 times 10 to the negative 19th coulombs, which I got by multiplying the elementary charge by 2. Please don't worry about memorizing this, though I will tell you, you may use it enough times that it ends up stuck in your brain no matter what. But even if you don't remember it, it is on the first page of your data booklet in that table of constants. So you do not need to worry about memorizing this number. Instead, the key is to know when to use it. So if we see proton or electron, your brain needs to automatically remember, oh yes, that has the elementary charge. Let me go back in my data booklet, look up the value of that, and now I know my charge, instead of seeing the word electron and assuming that charge is still an unknown. So with that, let's go ahead and do an example question. What is the magnitude of the electrostatic force between two electrons? And I'm noticing when I wrote this question, I forgot to give them a distance. So let's go ahead and say that they are separated by a distance of 2.3 micrometers. So let's go ahead and start by listing our givens and unknown. So I know that I've got two electrons. That means that Q1 equals Q2 equals E, the elementary charge, equals 1.602 times 10 to the negative 19th coulombs. I also know that R is 2.3 micrometers, or 2.3 times 10 to the negative 6th meters. If you don't recognize this symbol, whenever you see a symbol in front of my units that is a metric multiplier, you can always go back into your data booklet and look at the metric multipliers table. My unknown for this question is, of course, the electrostatic force. So my equation and my substitution and solution. I know the equation for electrostatic force is Fe equals K Q1 Q2 over R squared, or 8.99 times 10 to the 9th coulombs constant, times Q1 times Q2. So Q1 and Q2 are both 1.602 times 10 to the negative 19th coulombs. There's two of those, so I could just square the number, right? Because Q times Q gives me Q squared. And I'm going to divide that by R squared. 2.3 times 10 to the negative 6th meters, quantity squared. Throwing all that in my calculator, I get that the electrostatic force is 4.36 times 10 to the negative 17th newtons. And there we go. Next, we're going to talk about the electric field. So I know that the equation is here, and the unit that you are learning is E, electric field. In our previous video, we had electrostatic force by itself. In this case, we now have electrostatic field instead. And just like the gravitational field was measured in newtons per kilogram, so the unit for force, divided by the unit for the thing experiencing the field, in this case, the electrostatic field is going to be given in newtons per coulomb. So it's, again, that unit for force divided by the unit for the thing creating the field, which is charge, which we measure in coulombs. K is still 9 times 10 to the 9th, or 8.99 times 10 to the 9th. Here I'm using capital Q because I want to differentiate the charge generating the field from the charge experiencing the field. So that capital Q is for the charge generating the field, and R is the distance from that charge. So let's go ahead and take a look at a question. Calculate the magnitude of the electrostatic field, 1.03 nanocoulombs from the nucleus of a helium atom. So my givens and unknown, I know that the charge of my helium atom is 2e, or 2 times 1.602 times 10 to the negative 19th coulombs. I also know that my distance r is 1.03 times 10 to the negative 9th coulombs. And that 10 to the negative 9th comes from that n for nano. Next, I'm ready to identify my equation, sub, and solve. So my equation here is my equation for electrostatic field. E equals kq over r squared, or 8.99 times 10 to the 9th times 2 times 1.602 times 10 to the negative 19th, which is the charge of that atom, divided by 1.03 times 10 to the negative 9th quantity squared. When I put that in my calculator, I get that my electrostatic field is 2.72 times 10 to the 9th newtons per coulomb. And there we go. That is how I calculate electric field. The last equation I want to introduce is the equation that connects electric field and electric force. Fe equals QE. And again, just like how for the gravitational force, we calculated a gravitational force by multiplying mass times field. In this case, we're multiplying charge times field because electrostatic forces act on charges instead of masses. So I hope you guys throughout this video have been able to see that similarity between gravity and electricity, because that is one of the reasons that I teach both of these two topics together. So again, Fe is the electrostatic force, Q is the charge experiencing the force, the charge I put into the field, and E is the electric field. So let's take a look. An electron is placed in a uniform leftwards electric field of magnitude 17.3 newtons per coulomb. That's newtons times coulombs to the negative 1. First, we're going to determine the force on the electron, and then we're going to determine the acceleration of the electron. So let's go ahead and take a look. For part A, my givens and my unknown, I know that Q is my elementary charge E, 1.602 times 10 to the negative 19th coulombs. And that is going to be a negative charge. That's going to be negative. Now you'll notice in this case, I am being a lot more careful with my signs. And the reason for that is that when we talk about the direction of an electric field, this is the direction that a positive charge would move if placed in that field. So if my electric field is going to the left, like so, if I were to take a positive charge and place that positive charge somewhere in the field, that positive charge is also going to experience a force going to the left. If, however, I take a negative charge and I put the negative charge in the field, that charge is going to experience a force going to the right. So here, when I'm doing these questions involving fields and forces, particularly when I'm going from a field to a force, I need to make sure that I'm very careful with my directions. So moving on, the charge of an electron is negative 1.602 times 10 to the negative 19th coulombs, and my electric field E is negative 17.3 newtons per coulomb. That negative sign comes from the fact that this field is going to the left. So now that I've done that, I'm ready to do my equation and sub and solve. So looking at my equation, I know Fe is equal to QE. My electrostatic force is equal to charge times field, or negative 1.602 times 10 to the negative 19th times negative 17.3. Thus, my electrostatic force is going to be positive 2.77 times 10 to the negative 18th coulombs, or 2.77 times 10 to the negative 18th coulombs to the right. And that is how I'm going to solve for part A. For part B, I'm asked to find the acceleration of the electron. So I know that. So this one is asking you to connect what we've learned about here to the other things that you know about forces. So we know, of course, that F equals ma. And in this case, the only force that we've talked about is electricity. So the only force acting on this electron is the electrostatic force. So that means that the electrostatic force is equal to the mass of the electron times its acceleration. Now looking at this, your first instinct might be to say, Miss Gosling, I don't know what the mass of the electron is. But try to avoid that instinct. Instead, your instinct should be, seems like I need to know something that I don't know. Let's look at my data booklet, because guess what? The mass of the electron is on that same fundamental constants page that the elementary charge is on, and it's directly under the elementary charge. In fact, the mass of the electron is given from the data booklet as 9.110 times 10 to the negative 31st kilograms. So that means that the acceleration of the electron, A, is equal to the force the electron experiences divided by its mass, or 2.77 times 10 to the negative 18th divided by 9.110 times 10 to the negative 31st. When I set that in my calculator, I get that my acceleration is 3.04 times 10 to the 12th meters per second squared. And I'm also noticing that I actually wrote the wrong units for force. Force, of course, is not measured in coulombs, but in newtons. So for part A, your answer should have been in newtons. That's on me. So let's go ahead and take a moment to talk takeaways. First, electrostatic forces work only on charges. And the magnitude of the electrostatic force between the two charges can be found using Coulomb's law, F equals kqq over r squared. The elementary charge is another word for the charge of an electron or proton, and that value can be found in your data booklet. And it's very important to know that like charges attract and unlike charges repel. I'm just going to highlight that entire point because every word in there is fundamental to understanding this topic. So with that, you have now learned the basics of electricity. It is your turn to go out, try doing some problems. Best of luck and happy solving.